There is no specific requirement for the number of ground rods that must be added to achieve 25 ohms or less. The number of ground rods needed depends on the soil conditions and other factors such as the size and type of grounding system. Adding ground rods increases the surface area available for grounding, which lowers the resistance. However, it may not be necessary to add more than 2 ground rods if the first 2 provide sufficient grounding. According to the National Electrical Code, ground rods must be installed vertically. Horizontal installation is not permitted because it does not provide adequate grounding. The vertical orientation allows the rod to penetrate deeper into the soil, making contact with more conductive layers. When installing ground rods, the following recommendations should be followed. Firstly, use copper-clad steel ground rods at least 8 feet long and 5/8 inch in diameter. Secondly, space ground rods at least 6 feet apart. Thirdly, drive ground rods to the full 8 feet below grade. Fourthly, use a grounding clamp to connect the ground rods to the grounding conductor. And fifthly, test the ground resistance using a ground resistance tester. If the ground resistance is still too high after adding 2 ground rods, consult with a qualified electrician or grounding professional to determine the best course of action. Grounding is essential for electrical safety, providing a path for fault current to return to the source, tripping a breaker or fuse, and preventing electrical shock hazards. Ground rods are a crucial part of this grounding system. The goal is to achieve a low resistance path to earth, typically 25 ohms or less, to ensure effective dissipation of fault currents. Several factors affect ground resistance. These include soil resistivity, moisture content, temperature, and the type of soil. Rocky or sandy soil generally has higher resistivity than clay or loam. Soil resistivity is the measure of how well the soil conducts electricity. Lower resistivity means better conductivity. Moisture content significantly impacts soil resistivity. Dry soil is a poor conductor, while moist soil conducts electricity much more effectively. Temperature also plays a role. Freezing temperatures can increase soil resistivity. Soil composition varies widely. Clay soils tend to have lower resistivity due to their ability to retain moisture and the presence of conductive minerals. Sandy soils, on the other hand, are typically more resistive. The National Electrical Code, or NEC, provides guidelines for grounding and bonding to ensure electrical safety. The NEC outlines requirements for ground rod size, material, installation depth, and spacing. Compliance with the NEC is mandatory for all electrical installations. The NEC specifies that ground rods should be at least 8 feet long. Longer rods provide greater contact with the soil, reducing resistance. The diameter of the ground rod is also important. A common size is 5/8 inch in diameter, but the NEC permits other sizes based on specific conditions. Ground rods are typically made of copper-clad steel. Copper provides good conductivity, while steel provides strength and durability. Stainless steel ground rods are also available for corrosive environments. Ground rods must be driven into the ground to a depth of at least 8 feet. This ensures that the rod makes contact with stable soil layers and is protected from surface disturbances. If rock bottom is encountered, the ground rod can be buried in a trench at least 30 inches deep. The NEC requires a minimum spacing of 6 feet between ground rods. This spacing helps to minimize the overlap of their effective grounding zones. Closer spacing may not significantly reduce ground resistance. A grounding electrode conductor, or GEC, connects the ground rod to the electrical system's grounding busbar. The size of the GEC is determined by the size of the service entrance conductors. The GEC must be securely connected to the ground rod using a listed grounding clamp or connector. The connection must be protected from corrosion. Ground resistance testing is crucial to verify the effectiveness of the grounding system. A ground resistance tester, also known as a ground meter or earth tester, is used to measure the resistance to earth. Fall of potential method is a common technique for measuring ground resistance. This method involves driving 2 auxiliary ground electrodes into the soil and measuring the voltage drop and current flow. The ground resistance is calculated using Ohm's law. The 3-point test method is another common technique. It involves connecting the ground resistance tester to the ground rod and two auxiliary electrodes. The tester injects a current into the earth and measures the voltage drop. The ground resistance is then calculated. If the ground resistance is higher than 25 ohms, additional ground rods may be needed. Connecting multiple ground rods in parallel reduces the overall ground resistance. The total resistance of parallel ground rods is less than the resistance of any single rod. The number of additional ground rods needed depends on the soil conditions and the desired ground resistance. Installing additional ground rods involves driving them into the ground at least 6 feet apart. The ground rods are then connected together using a grounding conductor. The grounding conductor must be sized appropriately for the system. In some cases, chemical ground rods may be used to improve grounding in poor soil conditions. Chemical ground rods contain chemicals that leach into the surrounding soil, improving its conductivity. These rods require periodic maintenance to replenish the chemicals. Concrete encased electrodes, also known as UFA grounds, are another effective grounding method. A UFA ground consists of a length of bare copper conductor encased in concrete. This type of grounding system provides a large surface area for grounding. Grounding systems should be inspected regularly to ensure their effectiveness. Inspections should include visual checks of the ground rods, grounding conductors, and connections. Ground resistance should be tested periodically, especially after significant changes in soil conditions or electrical systems. Corrosion can damage ground rods and grounding conductors. Protect connections from corrosion using appropriate coatings and sealants. Replace corroded components promptly to maintain the integrity of the grounding system. Lightning protection systems require robust grounding to safely dissipate lightning strikes. Ground rods used for lightning protection should be installed in accordance with specific standards and guidelines. The grounding system for lightning protection should be separate from the electrical system grounding. Static electricity can build up in certain environments, such as industrial facilities and data centers. Grounding is essential to dissipate static charges and prevent damage to sensitive equipment. Special grounding techniques may be required for static control. In areas with corrosive soils, special precautions should be taken to protect ground rods and grounding conductors. Corrosion-resistant materials and coatings should be used. Regular inspections and maintenance are essential. In cold climates, frost heave can damage ground rods. Install ground rods below the frost line to prevent damage from frost heave. Consider using expansion couplings to accommodate movement caused by frost heave. Grounding is a critical aspect of electrical safety. Proper grounding protects people and equipment from electrical hazards. Consult with a qualified electrician or grounding professional to ensure that your grounding system meets all applicable requirements. Always follow the National Electrical Code and local regulations when installing and maintaining grounding systems. Regularly inspect and test grounding systems to ensure their continued effectiveness. Addressing high ground resistance may require several strategies. Firstly, you can add more ground rods to increase the contact area with the earth. Secondly, consider using chemical ground rods to improve soil conductivity. Thirdly, ensure proper spacing between ground rods to avoid overlapping grounding zones. Fourthly, improve soil conditions by adding conductive materials or moisture. Fifthly, consult with a grounding expert for a comprehensive assessment. The advantages of vertical ground rod installation include deeper penetration into the soil, access to more stable soil layers, and compliance with NEC standards. The disadvantages may include difficulty driving rods in rocky soil and potential for frost heave in cold climate. The advantages of horizontal ground rod installation include easier installation in shallow soil conditions and reduced risk of bending or breaking the rod during installation. However, horizontal installation is not permitted by the NEC and may not provide adequate grounding. Proper grounding is not just about meeting code requirements. It is about ensuring the safety of people and protecting valuable equipment. A well-designed and maintained grounding system is an investment in safety and reliability. Continuous improvement of grounding techniques is essential to keep pace with evolving electrical systems and environmental conditions. Stay informed about the latest grounding technologies and best practices. Attend training courses and workshops to enhance your knowledge and skills. Share your experiences and insights with others in the electrical industry. Proper grounding is a shared responsibility. By working together, we can create safer and more reliable electrical systems. When selecting a grounding location, consider factors such as soil type, moisture content, and proximity to underground utilities. Avoid areas with high soil resistivity or potential for corrosion. Choose a location that is easily accessible for inspection and maintenance. Consider the aesthetic impact of the grounding system and choose a location that minimizes visual intrusion. Grounding is a fundamental principle of electrical engineering. A solid understanding of grounding principles is essential for all electrical professionals. Invest time in learning about grounding and its importance in electrical safety. Share your knowledge with others and promote the importance of proper grounding practices. The effectiveness of a grounding system is directly related to the quality of its installation. Use high-quality materials and follow industry best practices. Pay attention to detail and ensure that all connections are secure and protected from corrosion. Take pride in your work and strive for excellence in every grounding installation. Grounding is not a one-size-fits-all solution. The best grounding system for a particular application depends on a variety of factors, including the size and type of electrical system, the soil conditions, and the environmental conditions. Consult with a qualified engineer to design a grounding system that meets your specific needs. Regular testing of grounding systems is essential to ensure their continued effectiveness. Testing should be performed at least annually or more frequently in areas with corrosive soils or unstable soil conditions. Keep records of all testing results and take corrective action as needed. Effective grounding is a team effort. Electricians, engineers, inspectors, and facility managers all play a role in ensuring that grounding systems are properly designed, installed, and maintained. Foster collaboration and communication among all stakeholders to promote a culture of safety. Grounding is a dynamic field with ongoing research and development. Stay abreast of the latest advancements in grounding technology and incorporate them into your designs and practices. By embracing innovation, we can continue to improve the safety and reliability of electrical systems. In summary, achieving adequate grounding involves understanding soil conditions, following NEC guidelines, using appropriate materials and techniques, and regularly testing and maintaining the system. It is a critical aspect of electrical safety and should be treated with the utmost care and attention to detail. The initial reading using ground testing equipment provides a baseline for the grounding system's effectiveness. This initial reading should be documented. Subsequent readings should be compared against the initial reading. Significant deviations from the initial reading can point to problems in the grounding system. These problems can include corrosion or loose connections. If deviations are noted, a qualified electrician should perform a detailed inspection and make necessary repairs. Keep detailed records of all grounding system inspections, tests, and maintenance activities. These records can be valuable for troubleshooting problems and demonstrating compliance with regulations. The records should include the date of the inspection, the name of the inspector, the test results, and any corrective actions taken. The ultimate goal of grounding is to provide a safe and reliable electrical system. By following best practices and staying informed about the latest advancements, we can achieve this goal and protect people and property from electrical hazards. Remember to consult with qualified professionals and adhere to all applicable codes and regulations.